All right, so we are continuing our discussion on series and sequences. We've wrapped up everything that we're going to talk about sequences, which remember a sequence is just a set of numbers that have been placed in a specific order. And now we're about halfway through with this video of our discussion on series. And the series, remember, is when you take that sequence and you add up all the terms. In the last video, we looked at some specific notation associated with a series. We called it sigma notation. And sigma notation just provided for us the tools that we would need to add up the terms of a sequence. But what we found in that video is that if there are a lot of terms, that turns into a lot of work. And so this video is the answer to that problem, and the next video also. For two specific types of sequences, for an arithmetic sequence in this video and a geometric sequence in the next video, we're going to look at a formula that will enable us to find the sum a little bit faster. So with that said, let's take a look at our learning objectives and we'll get started. In this particular video, we're just focusing on arithmetic series. And so our only learning objective is to find the sum of an arithmetic series. Okay. Now, the way this works is I want to remind you of some things that we already know. First, we already know that arithmetic series will have a general formula an arithmetic sequence will have a general formula that looks like a sub n equals, and I believe we use the variables r, n plus a naught. And so we talked about that this looks like the equation of a line. Okay. Now, why is that important? Well, because of the second thing that we know. So this is the first thing that we know. The second thing that we know is we know in sigma notation, there's going to be a formula right here. There's going to be a formula. And so if we have something that looks like this, just to make up some numbers, and then I put in a formula here, as long as that formula has a linear format to it, then we know that it must be arithmetic. And so these two facts together are what are going to enable us to be able to distinguish when we have an arithmetic series from some other kind of series. Okay, so this video focuses on the formula for things that are arithmetic. So what you will be looking for in this video and with the homework assignment that goes with this video is you'll be looking for the formula over here being something that's linear. And remember, linear means it's going to look something like mx plus b, something along those lines. So we're going to have our rate of change, slope, whatever you want to call this thing over here. You're going to have the spot where you're plugging in your numbers, the variable, and then you're going to have this constant at the end, the step 0 or the y-intercept or whatever you want to call that. And so as long as you have that format, then we know it's arithmetic. And if it's arithmetic, then there's a process that we can go. Now, I'm going to kind of do like we did when we talked about how to derive these formulas. I'm going to give a little bit of the background in this video with arithmetic, but then we'll do a video that has examples, and that goes pretty fast. And for the geometric, I'm not going to go through that background again. We're just going to kind of assume that we're good with this. So here's a little bit of background. And I talked a little bit about this in the last video when we did a series. So let's just suppose, for the sake of discussion, that I'm going to find the sum of the first 5 terms of this particular series. Let's just take that one, 2n plus 3. And from the last video, we know that what we're going to do with this is we're going to plug in the number 1. So I'll have 2 times 1, which is 2, plus 3. That's 5. And then we're going to plug in the next integer, which would be the number 2. So 2 times 2 is 4, plus 3. That's 7. And then I'll plug in the next one, which would be a 3. 2 times 3 is 6, plus 3. That's 9. And then when I plug in a 4, 2 times 4 is 8, plus 3 is 11. And last but not least, when I plug in a 5, I end up with a 2 times 5, which is 10 plus 3, and I get 13. Right? Now, what I pointed out last time is to notice that the 5 and the 13, if I add 5 plus 13, I'm going to end up with 18, right? And that was something that I pointed out last time. If I add the 11 and the 7, 7 plus 11, that is going to be equal to 18. And then I could also flip this over here, the 5 plus the 13, that equals 18. And the 7 plus the 11, well, that equals 18. And now in this particular example, I only have a 9 in the middle. So let's just add 9 to itself. Notice I'm going to end up with 18. And so realize what I've done is I've taken my original series that I've had here, and I just wrote that original series backwards. Instead of starting with 5, I'm stopping with 5. Instead of 7 coming next, 7 is the second to the last. 9 is still in the middle, and then the 11 and the 13. All I've done is I've written it backwards. And if I write it backwards and I add all the terms together, every single time I end up with an answer of 18. And 18 plus 18 plus 18 plus, that's going to be equal to 5 times 18. And 5 times 18 is 90. Now, that's all fine and good, but you probably can figure out very quickly that 5 plus 7 plus 9 plus 11 plus 13, that's not equal to 90, okay? Let's just look at that and take a look at that and see what is that equal to. So 5 plus 7 plus 9 plus 11 plus 13, that turns out to be equal to 45. 45, which notice is exactly half of 90. It's exactly half. 90 divided by 2 is equal to 45. It's exactly half. So is that a coincidence that the actual answer is exactly half of what I got when I added these 18s together? And the answer is no, that's not a coincidence. The reason that happened is because I took my sequence and I just added the sequence to itself in reverse order. So basically I have this thing plus itself. Well, anytime you add something to itself, that's the same as doing a times 2. So this 90 is equal to the sequence times 2. And if I just go backwards, then I can divide by 2, and that's going to give me my answer 45. Okay, now that's a very long, somewhat convoluted process. And you might be thinking, well, who would ever do this? And this is weird. And why would you do this? And whatever. It actually turns out that there's a pretty famous story in math history about an elementary schooler. His name was Gauss, and his teacher assigned him to add up all the numbers from 1 to 100, thinking it would take him a very long time to do it. And basically the teacher was giving him busy work. But Gauss did it in like less than 5 minutes, because Gauss recognized that if I just flip the numbers like this, I can get the answer very quickly by multiplying this together and then just dividing by 2 at the end. And that really becomes the process that we use, the process that has become our formula for solving these types of problems. Okay, so that's just a little bit of a background that talks about where the formula comes from. That's not something I would ask you on a test. Let's get to what the actual formula is. The formula for the sum of an arithmetic series is, and here's how that formula works. We're going to take the first term, whatever the first term is, okay? I'm going to actually, instead of calling it A1, I'm going to call it A first. A first. And you'll see why that is in a minute. So I'm going to call it A first. So I'm going to take the first term, and I'm going to add that to the last term. So I'm going to call this A sub last, okay? A sub last. So the first term plus the last term. Then I'm going to take this, and I'm going to multiply by n, when n is going to be equal to the number of terms. Now, as a side note, the hardest part of this process is figuring out what n is. So we're going to talk about that in a minute. But capital N is the number of terms. And then we're going to divide this whole thing by 2. And this will be equal to the sum. This will be equal to the sum. Okay. Now, let's start with just an arithmetic series where we can see all the terms and life is good and simple so that we can see that this works and verify it. Okay. Now, let's suppose that my series is 6 and 12 and 18 and 24. Okay, so just verifying that this is arithmetic. Remember, in arithmetic, the pattern as you go from term to term is that you're adding the same number over and over again. So 6 plus 6 equals 12, 12 plus 6 equals 18, 18 plus 6 equals 24. Yes, I'm adding the same thing over and over and over again. Okay, now there's only 4 terms here. There's not a lot. So you could grab your calculator and you could find the answer to this very quickly if you wanted to. In fact, I'm going to do that right now, just so that when we're done, we can verify that we got the actual right answer. So we should end up with 60 when we're done with this. All right. But what I'm going to do is I'm going to use this formula. I'm going to say that this is going to be equal to the number of terms. So how many terms are there? There's 1, 2, 3, 4 terms. The number of terms times the term that comes first. Well, that's 6. Plus the term that comes last. That's 24. And then all divided by 2. That's how my formula works. Now I just use order of operations. I've got to start with inside the grouping symbol. So inside the grouping symbol, 6 plus 24, excuse me, 6 plus 24, well, that's equal to 30. And then if I multiply 4 times 30, I'm going to get 120. And 120 divided by 2 is equal to 60. And that is exactly the answer I got. Okay. Now, with only 4 terms, you might be thinking, isn't it faster and easier just to type it into my calculator? And the answer is yes. Yes, it is. So let's talk about why would I use this, or when would I use this? We would use this when we have more terms, when we have lots of terms. So let's suppose that I've got a situation where I'm not going just for 4 terms, like this one, just 4 terms, okay? Oh, I didn't mean to make this a capital N. Let's change that real quick. I don't want it to get confused with the N in our formula. And typically when we're working with sigma notation, whatever right here, that's going to be a lowercase letter. So let's make it a lowercase n, okay? Now let's say we're going to do this for 100 terms. Now I'm not going to want to just type this into my calculator. I'm not going to want to do that. So next to the sigma notation, there's going to be a formula. So let's say our formula is 5n minus 17. There's my formula. Okay. Now, with the video that I made last time, we would plug in a 1, and then we'd plug in a 2, and then we'd plug in a 3, and then we'd plug in a 4, and we'd have to do that all the way till we got to 100. So we have to do that 100 times. And then we'd have to add all those numbers up. That's a lot of work. With the formula that we've written down here today, we can skip most of that work because all we need to know is the first term. So how do I figure out the first term? I'm going to plug this number in. Okay, so a sub first is going to be 5 times 1 minus 17. 5 times 1 is equal to 5 minus 17. That's going to be a negative 12. And then I need to know my last term. So a sub last is going to be when I plug the 100 in. So that's 5 times 100 minus 17. So 5 times 100 is 500. Minus 17 is going to be 483. 483. Okay, so now I can plug those numbers into my formula. Negative 12 is my first term. 483 is my last term. Divided by 2. All I have left to do is figure out the number of terms. Okay. Now, on this particular problem, it's not too bad. If I'm going from 1 to 100, there's going to be 100 terms. Okay. And that should make sense to us, right? If I went from 1 to 1, there would be 1 term. From 1 to 2, there would be 1 and 2. Well, that would be 2 terms. If I did 1 to 3, there would be a 1, there'd be a 2, there'd be a 3. So that would be 3 terms, et cetera, et cetera. So if I start at 1, the number of terms is just simply going to be whatever number's up there at the top. Fairly straightforward, pretty easy to do. And now this, I can just type into my calculator and solve, or I can use order of operations, whichever. I'm going to opt to do it on my calculator. So 100 times -12 plus 483, all divided by 2. And I end up with a 23,550 for my answer. And that was a very fast, quick process. Okay, now for this video, there is one last thing that I want to mention. And I said it when I wrote the formula, that sometimes n can be the hardest thing to figure out on these problems. The first number is not too hard to figure out. You just plug in whatever the first number is, and that gives you your first term. The last term is not too hard to figure out. You just plug in this last number, that gives you the last term. N can be the hardest thing to figure out. And to point out why that's true, what I want to do is look at some of the problems that we've done in previous videos. So at the beginning of this video, we did this problem where I went from 1 to 5, okay? And so notice going from 1 to 5, there was 1, 2, 3, 4, 5 terms. I had 5 terms. So my capital N would be equal to 5, which is pretty straightforward if I'm going from 1 to 5. But in the last video, we did a problem that looked like this, okay? From 3 to 12. Now, I'd like you to just think, not even looking at my work here from the last video, think about how many terms would there be if I go from 3 to 12? Okay, well, what a lot of people would do is they would say, well, 12 minus 3, that's equal to 9. So they'd say there's going to be 9 terms. But let's look and see how many terms we actually ended up with. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, we had 10 terms. We had 10 terms when we did that. Okay. Now, let's take a look at this one. If I go from 6 to 8, some people would look at that and they would say, oh, that's going to be, whoops, 8 minus 6, that's going to be 2 terms. But if you think about it, plug in 6, plug in 7, plug in 8, that's obviously going to be 3 terms. Okay, so the trap that people fall into is sometimes they think if I just subtract these 2 numbers, that's going to tell me how many terms there are. 5 minus 1 equals 4. Oh, but there wasn't 4, there was 5. And so notice there's this consistent pattern. If I subtract the 2 numbers, the bottom minus the top, but then add 1, 5 minus 1 equals 4 plus 1, there's my right answer. Okay, bottom minus the top. In this case, bottom minus the top would be 8 minus 6, but then if I add 1, I'd have 8 minus 6 plus 1. That's going to be 2 plus 1. That's 3. 3 is the right answer. Okay. And same thing with this. If I were to do 12 minus 3 plus 1 for my bottom minus the top plus 1, this is equal to 9. 9 plus 1 is 10. That's the correct number of terms. Okay. So bottom line, going back to our formula here, generally speaking, you can find the number of terms by doing the top number minus the bottom number and then plus 1. You know what? I think on all of these things I said bottom minus top. I was doing top minus bottom. So I said the wrong, I wrote the right thing, but I said the wrong thing. It should be top minus bottom. Top minus bottom. The number at the top of my sigma notation minus the number at the bottom of my sigma notation, and then plus 1. Okay, so that takes care of what the formula is and the basic idea of how the formula works. I'm going to wrap this video up here. I will make a second video that has a couple of examples using this formula so that you can get a few more examples if you want them. But that's it for this one. Thanks for watching. Have a good one.